Okay, I've got a filter here which is a curious thing. It's going to have staircase gain but also staircase group delay, and my task is to do equalization of it. I'm going to do that in two parts. Here's the model with the filter under test shown here in red, and you can see the staircase sort of indication here on the icon. And we're going to look quite closely to that block right now and just see what sort of distortion it's responsible for, and the remainder of the model we'll examine more as we go downstream of that, and that will be attempting to remedy this bad behavior. So if we start the model running, drill down to scope 1 and suppress the yellow, we can see the white is the incoming trace here, which is the incoming chirp. You can see quite wideband, very ripply, and all the rest. But what comes out is, of course, highly distorted. I look at that by itself, and we see that it's quite spread out. The thing is rolled up terrifically in frequency, just quite a mess compared to what it started off as. Now, if we were to make any headway, it's very useful to do an impulse test on this, and so we do. This is what we've got coming in now. The impulse you can just about see at the left-hand side in white. Very much spread out. Interesting little structural elements of this thing you could probably imagine. But the important thing is that this flat spectrum of the incoming impulse has been rolled up to on these three different plateaus here. Now, we've only got magnitude information here, but this is typical of what you might encounter in a lab situation where you might have just a scope with no way of measuring phase, or you might have a spectrum analyzer that doesn't give you things like group delay and phase. So we have to do the best we can with this information. So let's get it into our system by exporting this from the scope to the profile calculator. Now it's the trace 1, the yellow, that we're interested in. And this is the situation. Minus Nyquist, DC plus Nyquist. And here's the plateaus I mentioned. This is the thing which is causing the trouble. We'd like to have the fixer for this, and of course that's going to be the inverse magnitude, and that can be easily obtained here. Noting that this is on plot A, we can do 1 over A and memory store that into plot B, and you can see here the upside down of A, and that's the thing that we're hoping to be able to design. I have a filter lying in wait for that. It's going to be inside Slifer, so I'm going to dispatch this profile right here to Slifer. It's going to be the one on trace B, so off it goes. And here's Slifer now showing us what it's got. It's received that red profile, and here of course is DC Nyquist, but it's not doing too grand a job because it's got a very small number of coefficients. So let's make this hug a bit better. Let's go up to here, let's say 61 coefficients, and see what happens. Well, of course we get an objection. The objection is from Simulink, because fair enough, it can't change its net list at runtime, so it needs us not to be going and changing coefficient numbers. We can change the values. So let's bring that to a halt right now, make sure this thing has been received, and sure enough we see now with 61 coefficients a much more respectable fit for our inverse gain fixer. Let's see if it's actually done any good. We'll go down through the Slifer, which is this block, and then observe it on Analyzer 2 and see what's happened. I look now on Analyzer 2 and I see, well, I'm gloriously happy with this spectrum situation because the yellow is hugging the white very nicely. I look at the time domain, I'm less enamored by this. So here's my impulse, here's the impulse response, and it's quite spread out. Obviously not too healthy result. We might just put the chirp through that to see what we see from there. We are gratified to see that the yellow falls on top of the white yet again, looking very good spectral magnitude wise. But let's line these up. I've got an analyzer, a delay block right here, which I can bring into play, and I can bring this on up and try to see just where the onset of this. I'll line up these pulses right here. Yeah, okay, so there's my input lined up with my output, and you can see it's spread, really mishmashed quite a lot, even though the spectrum magnitude looks quite wonderful. So we do not have the final situation at all. Let's go back to the impulse. Let's get rid of this. We don't need that anymore. And let's start thinking about an additional fixer, which is going to try to take care of what must be a problem with group delay. Well, we need to find out the group delay. Luckily, we've got it instrumented. There is an analyzer right here which is hooked into the entrails of this system right here and is actually able to calculate the group delay. It's a CPIG analyzer, and you see that's the gain that we had a while ago, but we tune in group delay. Look at how the shape is almost the same. Even the numbers are the same, except now this is a scale in terms of group delay in samples. Here according to DC out to Nyquist. We could have group delay in seconds, but that's not nearly as informative to us, because when we see this mid-span value of about 50 and this sort of symmetric behavior about that, well, we start feeling pretty good. We start thinking we probably could build a way to emulate that all-pass filter or that group delay with an all-pass filter of a size of about 101 coefficients, more or less double of what the mid-span is. Well, of course, it's not going to be that we want. It's going to be sort of like an inverse. Let's just take that across to our working area and our old friend the profile calculator, and here it is, a shape greatly similar to what we had before, and this is the thing we're interested in. But I'm going to concoct now the negative of this, because this is the kind of inversion we need now. It's an additive complement that we want to have. So what I'm going to do, I'm going to clear the accumulator down here, and I'm going to take minus A, and I'm going to put this onto trace B. So here's this now turned upside down and looking pretty good, except for the fact that it's all biased down here very negatively. That's no good, because we're going to have some sort of delay which will bring this up to a causal filter. So I'm going to add 100 samples worth of delay onto that. I'm just typing this in. I'm going to put that on trace B. Look at it now. It's biased up here, and its mid-span area is about 50, which is reassuring to me. Well, that's the group delay, but since my task is not to disturb the magnitude, because we're quite happy with that from the thing that we just previously saw with our Slifer filter, I'm going to make this an all-pass filter, this second segment. I'm going to clear the accumulator, put a 1 into A, and this will be the gain that I aspire to, and this will be the group delay that I aspire to in my equalizer. Well, luckily I have a utility for doing this. I'm going to clear the accumulator and bring that in by pushing this button. This is gain and group delay to magnitude, and the gain has got to be on this channel, the B has got to be on that plot. I'm going to devote 101 coefficients, as I've already told myself I think that's going to be a good result. I button this in, and now I create and in fact deposit on trace C the corresponding magnitude. You notice it's two colors for the real and imaginary part of the target's magnitude. Okay, all well and good, but we've got to now design to this. We're going to allot this task to Sketch-a-Filt. So we now dispatch this by sending a profile, which one? C. And it goes to Sketch-a-Filt. And let's look and see what has happened as a result of all this. I'll put it on linear. Quite a nice flat gain, it looks like, and quite a wide sort of impulse response coming up here. I could just check this. It's being implemented by a frequency sampling filter, and there it is, looking very, very nice. Group delay wise, well, it seems to be more or less what the doctor ordered here. So let's just see what it actually does when the signal runs through our first part of our fixer and the second part of our fixer, and what do I get? absolutely wonderful. Here's my input. Okay, we've encountered delay, typical thing with a distortionless system, but just look what's happened here. Let me put the chirp in just for good measure, and I see that good behavior here, but also now good behavior in the impulse response. So I've managed with just a few maneuvers here to separately fix the gain, separately fix the group delay, and to successfully equalize our filter under test.